I'm Talia Prendel.
Hi, I'm Tyler Thompson.
Hi, I'm Shannon Sire.
And I'm Michael Bruce, and we are the team working on the Open Energy Dashboard Time Varying Conversions update on the server side. Let's get started. We were advised by Stephen Huss Letterman, overseer of the OED project.
OED, short for Open Energy Dashboard, is a free open source web application that helps organizations visualize their energy and resource data. Version 3.00 will introduce time varying conversions, for example, tracking costs that change over time. Preparing for this new version required optimizing the existing database SQL logic to maintain performance standards and adding backend components to support the updated UI the front end team was building. One of the major focus areas was the database and API developed in collaboration with the front end team. The PostgreSQL schema and SQL were updated to support day and week time varying conversions. Over 25 new admin only REST API routes were created, and a Postman OED collection was built to keep endpoint testing organized. Each route includes its purpose, query parameters, and example request and response. This collection and documentation have been handed over to OED so the team can continue using it and adding new routes in the future. For example, if you wanted to see an example of adding a day pattern, you would go to the left here, go into the folder. For day patterns, select Add Day, and here you can see the endpoint URL, the purpose, any authorization needed, query parameters, and an example request and example response. This collection and documentation have been handed over to OED so the team can continue using it and adding new routes in the future. Key challenges included ensuring continuous time coverage without overlaps, resolving legacy code conflicts, and addressing differences in how PostgreSQL and JavaScript handle infinity values.
We began by building on the previous group's implementation. Rather than embedding the conversion logic directly within the graphing function, we refractored it into a materialized view. This allowed hourly conversions to be pre-computed and stored for improved performance. Additionally, a daily materialized view was created to store daily aggregates of the converted hourly data. Notably, the daily view does not apply conversions directly. Instead, it aggregates the already converted hourly values. The graphing functions were updated to retrieve converted readings from these views, eliminating the need to apply conversions on the fly during each query. After building the initial views, we tested, timed, and documented multiple index configurations to see which ones would give the fastest query times. From our analysis, we selected a composite index that works for both hourly and daily and is defined on the meter ID, graphic unit ID, and lower bounds of the time interval. This index provided the most consistent performance improvement across the relevant queries. During testing, we found that our hourly view only worked when a single conversion was being applied to a reading, or conversions of equal length. If the conversions had unequal lengths, or if they partially overlapped the reading, the results became inaccurate. This implementation was also dependent on the old view that stored the unconverted hourly readings. To solve this, we created a new hourly view, which uses a common table expression to store the unconverted hourly readings and uses the intersection between the conversion and a reading to apply a weighted average conversion. This solved the aforementioned issues, but further testing revealed that there was a loss of precision due to applying conversions to an average hourly rate. It was also impossible to derive accurate minimum and maximum ranks without referencing the raw data. To address this loss of precision, we created an additional materialized view that applied conversions directly to the raw readings and stored the results. Then we developed a new hourly view, which aggregates converted raw readings into hourly data, similar to how our daily view functions. This approach eliminates the need to apply conversions directly at the hourly level, since the raw readings are already converted and the hourly readings became an aggregate of those converted values. However, after observing several test cases, it became clear that this method also had its limitations, albeit somewhat of an inverse of the previous approach. When raw readings span across multiple hourly partitions, the hourly aggregates no longer reflect only the conversions that apply within the specific hour. Instead, they also include the effects of conversions applied to the portions of the raw readings that lie outside the hour being analyzed.
Considering the potential loss in performance by adding time-varying conversions, we tangentially investigated the viability of a Postgres extension called TimescaleDB. It would theoretically provide higher quality indexing for time series data and potentially allow for partial rebuilds of materialized views, which could improve performance. Due to a lack of viable Postgres Docker images with Timescale installed, we also had to rebuild the dashboard on top of an upgraded version of Postgres. While we made progress towards incorporating the time series features, there was still significant logic changes that needed to be redone on top of Timescale's hypertables. Even after those changes are added, there is still more testing to prove the time savings are worth the added overhead of Timescale. We left documentation for the next team that will pick this up and can fully realize TimescaleDB and Postgres 17 as an option for OED in the future.
Testing was coordinated with project leads across 3 areas: admin UI endpoint, materialized views, and timescale DB. We built on tests provided by the leads and created new ones where needed, streamlining execution and ensuring reproducibility. We also leveraged AI-assisted development using tools like ChatGPT, Gemini, and GitHub Copilot, alongside traditional research and prior coursework to design and refine our tests efficiently. For one of our performance tests, we use a test suite with a main script, reconfiguration, time refresh views, and time function queries. The configuration file defined functions, materialized views, and parameters, allowing both multi-parameter and single-parameter tests. In addition to performance testing, one method for validating accuracy under development is running test cases and verifying results by copying, importing the output into a pre-configured spreadsheet, which calculates and verifies the results, making the results easy to analyze and quick to confirm expected values. As a team, working together on the OED project was a tremendously rewarding experience, and we were very grateful to have had the opportunity to contribute to OED. Some of us will continue to work on the project in the near future, while others, having left their mark, will move on, taking the benefits of the OED experience with them. Through this project, we gained valuable skills in back-end development, cross-team collaboration, query analysis, and algorithm design, implementing a major platform upgrade in parallel with new feature development, and combining traditional and novel approaches to developmental testing and research. We thank Steve Huss-Letterman from OED, Kayla Rolacek, Professor Robertson, Dr. Sue, and everyone at CSUMB for making our journey through the CS Online program truly exceptional. We leave CSUMB better prepared and more confident than when we first arrived.